Hi everyone. I'm going to be going over question 57 from the Chapter 7 Bingo questions. Now this problem has to do with this, this package that's being dropped down this ramp right here, and we're going to figure out some physics that involve that package as it's being dropped and it goes around this corner. So first of all, part A wants to know what the coefficient of kinetic friction is on this horizontal surface. So as you can see, I have points A, B, and C. Package starts at A, it goes down, hits this slope, and then from B to C, this is perfectly horizontal. And so part A wants to know the coefficient of friction for that part. So the way we do that is through using our energy equation. And so since it's just from B to C, we do know that kinetic friction is involved. So we'll put that up. And then since it's horizontal and it's horizontal, so there's no potential energy. So we don't even need to put the U here. But since there is friction, we know that there is a work being done. So we do need to add the work there. And then it said in the problem that at the end, at point C, it stops. Everything stops. And so there's going to be no kinetic energy and no potential energy. So it's just going to equal 0. Now, this is pretty basic, so what we'll do is we'll break both of these up into the components. So we know that kinetic energy is 1/2 mv squared. We know that the work we can break down into the negative coefficient of friction times mg times the displacement. And so since we've broken that up now, it looks like everything is what we have. So what we're looking for is this. So let's isolate that in our equation. So the way I did it is I just plugged everything in and then went from there. It was kind of easier for me to do it that way. So we know the mass is 0.2, so 1/2, 0.2. The velocity is 4.8 squared minus the coefficient of friction times the mass times gravity times the displacement, which is going to be 3 meters, and that equals 0. So we have that, and now we'll plug everything in and we'll end up with we'll end up with 1/2 times that's what I got, and then times that by 1/2 and divide this over, you get the coefficient of friction equals 0.39. So that's part A. We know that equals 0.39. And now we'll do part B. So part B wants to know, says how much work is done on the package by friction as it slides down the circular arc from A to B. So we're looking at this part right now instead of this part. So the way we set that up is, once again, through our energy equations. So we'll do, okay, a point A, which actually don't even need to put that because its starting point is from rest, so there's no kinetic energy at point A. So we'll just put, we'll just start with UA plus work equals, at part B, if you remember, there's no potential energy, only kinetic. So we'll say KB. Then from there, we can break up these things. So our potential energy can be split up into mg radius plus the work equals, and we know that kinetic energy is 1/2 mv squared. So from here, now what we can do is, and this is going to be the velocity at B. Really from here, we just plug everything in. It's really that simple. So the mass is 0.2. Gravity is 9.81. The radius was given to us in the problem. It's 1.6 meters. Plus work equals 1/2 times 0.2 times the velocity at point B is 4.8 squared. Now when we plug all this in, we end up getting the work, which is the only variable in here now, the work equals negative 0.84 joules. And that makes sense because we, since this is our positive direction to the right, we are expecting the work to be done in the negative direction. So it makes sense that it's negative, which is always good to check that. But yeah, everything looks good. So hopefully you learned something, and I'll see you in the next video. Thanks for watching.